So based on looking at one specific example of a linear transformation, we have an idea for a theorem, a hope for a formula. And our hope is this, that for a linear map from V to W between finite dimensional vector spaces, the rank of the map plus the nullity of the map equals the dimension of the domain space V. So how could we prove this? So I guess we'll be optimistic and give this a name with theorem in it. We'll call this the rank nullity theorem, but keep in mind that we haven't actually proven that it's a theorem yet. So how could we prove this? Well, this is all about counting dimensions, and how do you deal with dimensions? You have to deal with a basis, right? Because a dimension is the number of elements in a basis for a space. So maybe what we should do is come up with a nice basis that will let us handle these situations. And there are two spaces where you might think about bases. You might think about bases in V or in W, but it's hard to know which way to start in V or in W, but I mean, rank is the dimension of the image, so this is sort of happening in W. Nullity is the dimension of the null space, that's happening in V, and then, of course the dimension of V is happening in V. So 2 out of the 3 are in V, so maybe we should think about a dimension, maybe we should think about a basis in V. Another reason why it's a good idea to start with the basis in V is because our function starts in V, so maybe we should start thinking about V first. Now, whenever you choose a basis for a situation, right, there are lots of bases that you might choose for V. You could just say let V1 to Vn be a basis, but just choosing an arbitrary basis doesn't necessarily mean that your basis is somehow well adapted to the problem that you're dealing with. So since we're dealing with a specific subspace, right, nullity, this is the dimension of the null space of F. Since we're dealing with a this is in V, this subspace is in V, since we're dealing with a specific subspace of V, maybe we should choose a basis that somehow is adapted well for this subspace. And that is indeed what we'll do. Just to name these things so I don't have to write out nullity and dimension all the time, let's say V is dimension n, nullity, let's say it's k, then we want to show, ultimately, that the rank of F is n minus k, right? If we can show that, then we're done, because we'll have proven this formula. Okay, so we need to come up with a nice basis. Well, let's start with the null space. So let's let beta 1 through beta k be a basis for the null space. Okay, the null space is a subspace of V, so we can choose a basis for it. But also we know that if we have a linearly independent set in V, we can extend it to a basis. So let's extend to a basis beta 1 up to beta k, so we're keeping the same first k vectors, but then we're adding on some others, beta k plus 1 up through beta n, to a basis for all of V. Okay. Now, this function, because these beta 1 through beta k, right, we know what the function does to all of these. Beta 1 through beta k are a basis for the null space, so F sends all of these to the 0 vector in W, right? So how many vectors are left over in this basis? Well, there's n minus k, which, right, that's a very suggestive number because it seems like if the rank of this map is n minus k, that means we should come up with a basis for the image of F with n minus k vectors. Well, here's n minus k vectors. It's just these are all in V, and we're looking for a basis for the image that lives in W. So somehow we need to transport these things over to W. Well, how do you transport vectors from V to W? You use the linear map, right? That's the only way to do it in this situation. So let's let W, so my indexing is a little strange. I guess I'll write it like this. Let's let W k plus 1 be f of beta k plus 1, and so on, all the way up to wn, which is f of beta n. So we have to keep in mind that these w's, there are n minus k things here. So there are n minus k w's, because we're starting with k plus 1 and going up to n. So there are n minus k of these. And I'm doing it this way just so that the index on my w matches the index on the corresponding beta. I'm not sure that's the best way to do it, but that's the way I'm going to do it. So we have these n minus k vectors in w, right? All of these w's are vectors in capital W. Probably we should hope that if the universe is kind to us, these w's from wk plus 1 up to wk are a basis for the image of this map. If they are, if these w's are a basis for the image of our map, then we're done, because we have a basis for the image that has n minus k vectors in it, and that means the dimension of the image would be n minus k, so the rank is n minus k. So if this is true, if these really are a basis, we are done. Well, what do we need to show for them to be a basis? We need to show they span, and we need to show they're linearly independent. So first, let's ask ourselves, do these w's span, this should be up to n, do these span the image of f? Okay, well, how can you check? Well, we need to take a vector in this image and see if we can write it as a linear combination of the w's. So let's take w in the image of f. Since w is in the image of f, that means that there is some v in capital V, so that f of v is w. Right? That's the definition of image. To be in the image, you have to get hit by the function. So there has to be some v that hits w. All right. Well, remember, we have a basis for the vector space capital V. So let's write our vector little v as a1 times beta 1 plus dot 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 plus an times beta n. Right? That has to be possible because remember, the betas are a basis for capital V. All right, so we know that w is f of v. That was just the definition of v. But now we have a different way of writing v. v is a1 beta 1 plus dot 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 plus an beta n. But f is a linear transformation, so we can use the fact that it preserves structure. So this is a1 f of beta 1 plus dot dot dot. Now I'm actually going to write out a couple more terms here. There's a sub k f of beta sub k, and then there's a sub k plus 1 f of beta sub k plus 1, and then so on down the line to a sub n f of beta sub n. Okay, so what is each of these? Well, remember, beta 1 through beta k, those are all in the null space of f, right? That's how we chose the beta 1 through beta k. So these first terms up to the kth term, f is, we're applying f to something in f's null space. That produces 0 by definition, right? So all of these terms, f produces 0 for all of these terms. So all of these terms are just 0. All right, what about these remaining terms? So a sub k plus 1. So what is f of beta sub k plus 1? Well, look up here. f of beta sub k plus 1 is w sub k plus 1. And so on down to a sub n times w sub n. So look, we've written w as a linear combination of wk plus 1 through wn. So this means that wk plus 1 through wn span the image of f. right? We took anything in F, we wrote it as a linear combination of wk plus 1 through wn. That means that wk plus 1 through wn span the image. All right, so that's half of what we needed. Remember, now we were trying to show that these w's form a basis for the image. We've shown that they span. Now we need to show that they're linearly independent. So r wk plus 1 up through wn linearly independent. Well, how do you prove something is linearly independent? Take a linear dependence relationship, show that it has to be the trivial linear dependence relationship. So let's write A1, sorry, let me index things so that they match. A sub k plus 1, w sub k plus 1, plus dot dot dot, plus a sub n, w sub n, right? And this is equal to 0 in w. So we need to, right, we've written a linear dependence relationship. We are hoping to show that all of these a's have to be 0. So how could we do that? Well, I mean, we don't have a lot of options for what to do here. Really, the only thing we can do is write the w's in terms of f. Remember, w sub k plus 1, that's f of beta sub k plus 1, and so on. So down to a sub n times w sub n is f of beta sub n. All right. Well, now that we have all these f's on the left-hand side here, we can use the fact that f preserves structure. So we can write this as f of a sub k plus 1, beta sub k plus 1, plus dot dot dot, down to a sub n, beta sub n. All right. Well, now look. We have a vector. We've hit it with f, and it produced a 0. That means that this vector is in the null space of f. So a sub k plus 1, beta sub k plus 1, plus dot dot dot, down to a sub n, beta sub n, is in the null space of f. But remember, we cooked up our original basis, the betas, so that the null space of f is actually spanned by beta sub 1 through beta sub k. So since this linear combination of beta sub k plus 1 through beta sub n is in the null space of f, that means this linear combination, a sub k plus 1, beta sub k plus 1, plus dot dot dot, plus a sub n, beta sub n, this has to be equal to a linear combination of the other betas. So a1, beta 1, plus dot dot dot, plus a sub k, beta sub k. Right? The left-hand side is in the null space, so it has to look like a linear combination of the basis for the null space, which is beta 1 through beta k. All right, well, now move everything to the left. Right? You can see what's coming. Move everything to the left. We get minus a1 beta 1, minus, and so on, down to minus a sub k beta sub k, plus a sub k plus 1, beta sub k plus 1, plus dot dot dot, down to a sub n, beta sub n equals 0. This 0 is in V, by the way. This is the 0 in V. And look, we have a linear dependence relationship, right? But this is a linear dependence relationship among the betas. But the betas, all the betas together are a basis for the whole space V. So this linear dependence relationship has to be the trivial linear dependence relationship. So that means A1 has to be 0, A2 has to be 0, all the way down to AN has to be 0. And in particular, this means that the a's that we started with, a sub k plus 1 down to a sub n, all have to be 0. So, right, way back up here, we wrote a linear dependence relationship, we just showed that it has to be the trivial linear dependence relationship. So the only linear dependence relationship among the w's is the trivial one. So w sub k plus 1 through w sub n are linearly independent. Okay, so now let's take stock of what we have. Right. We showed that the w's are linearly independent. Before that, we showed that they span the image. So we have a linearly independent spanning set for the image. So that means that w sub k plus 1 through w sub n are a basis for the image of f. So the rank of f is the number of elements in this basis, but that's n minus k. And that's what we needed to show, right? Since the k was our name for, so n was our name for the dimension of v, k was our name for the nullity of f, and then rearranging this gives the rank nullity theorem. So we did it. The rank nullity theorem is kind of surprising. So scrolling all the way back up to the rank nullity theorem, this is kind of surprising because, right, two of these spaces are subspaces of V, but the rank isn't, or the image is not a subspace of V. So I guess I should write null space of F is a subspace of V. V is a subspace of V. The rank is the dimension of the image, and the image isn't a subspace of V at all. It's a subspace of W. So this equation, the rank nullity theorem, is surprising exactly because it relates subspaces that don't live in the same larger vector space. So that's why this is important.